Hello, and welcome back to another lesson in calculus. Today, we're going to be looking at continuity and discontinuities and trying to figure out when a function is continuous and where it might not be continuous. So, when we talk about continuous functions, think to yourself, what does it mean to be continuous? And there is official mathematical vocabulary that we could use, but we're going to get to that continuous part in a minute. But right now, up to this point, continuous function kind of just means that there are no breaks or holes in the graph. And if you look at a function or look at a graph and there's no breaks or holes in it, it's continuous. Another way you can think about it is if you can draw the entire function without picking up your pencil. So look at this function to the right. I can draw this entire function without picking up my pen, just like that. It's a nice, smooth, continuous function. Down here, these are not continuous functions because they have breaks and holes in the graph. This one right here, I can draw this portion of it, but then once I get to here, because it's a hole, I have to pick my pen up and then I have to draw this portion of it. So this is not continuous because it has this missing point. This one over here is not continuous because I can draw this portion and then I have a break in the graph called an asymptote, and then I can draw this portion. So these two are non-continuous while this function up here is continuous. So in order for a function to be continuous, three conditions must be upheld. Okay? So the first condition is f of c must be defined. Now, when we're talking about this, we're talking about continuous at the point or the x value of c. Okay, so we're talking about, is this function continuous at the x value of c? So if it's continuous, then the point is actually defined. Condition number two is that the limit, as we get closer and closer to the x value, is also defined or exists. Okay, so the limit has to exist. It can't be, does not exist. And then the third condition is that these two things are equal to one another. So when I find f of c, it should equal the limit as x approaches c of the function. If these two are equal, then that means that the function is continuous at that particular point. So let's look at an example. These are three functions. All three of these are not continuous, so we're going to find out why. So looking at this function, we can see that the function is not continuous at the x value of 1. So it's discontinuous at x equals 1. Well, let's look at why. So if we go through our three conditions, f of c is defined. So what is f of 1? Well, if I look at the function, f of 1 is this point right here. It's not that point, that's a hole. It's that point. So f of 1 is 0. Okay, so that's condition 1. Condition 2, the limit as x approaches 1 of my function. So with the limit, as I get closer and closer to the x value of 1, you see I approach it this way, and I can approach it this way. And the limit as I approach 1 is 1, because this is where the function is supposed to be. Now, because these two are not equal, it's discontinuous at that value. Okay, so back to our conditions. F of c is defined. Well, f of c is defined. F of 1 is 0. It is defined. The limit exists. Well, the limit does exist because the limit is 1. However, the third condition is not upheld. The function value does not equal the limit because 1 does not equal 0. Okay, here we have it's discontinuous here at -1. It's discontinuous here at 1. Okay, And for many reasons, we could talk about at x equals -1 and x equals 1, you can see that both times the limit, I'll do a different color. The limit as x approaches -1 of my function, so as I get closer to -1 from the left and from the right, you'll see that they approach different values. So therefore, the limit does not exist. And therefore, it would break my second condition, which says the limit must exist. But the limit does not exist, so therefore it can't be continuous there. For this portion right here, I'll put it in black, I can do the same thing. The limit as x approaches +1 of my function, so as I approach it from the left and from the right, you'll see that I approach different numbers, and therefore the limit does not exist. So I have a break in my graph. So in this graph, I have 2 points of discontinuity. And lastly, this one, there's an asymptote here. So because there is an asymptote, the condition that I'm breaking is condition number 1, because f of 0 does not exist. So the only way that a point can be continuous is if f of c is defined, but f of 0 is not defined, so therefore we are discontinuous at the x value of 0. So there's my points of discontinuity. So there are different types of discontinuity. So the first is a removable discontinuity. A removable discontinuity is a hole that is created in the graph. Okay, a hole is represented by an open circle. Okay, so in these examples, the limit could exist, but because there is a hole there, so if you look at this guy right here, because there is a hole at this point, right, that means that it is discontinuous at the x value of 2. So I have removable discontinuity at x equals 2. That's because there's a hole there. And the reason why it is a discontinuity is because the function value is 8, but the limit is 4, so they don't equal one another. So it is discontinuous. And the type of discontinuity is a removable discontinuity. And the same thing can be made for this example. Okay, I have a removable discontinuity right there. It is a hole, so I have a removable discontinuity at x equals 2. Okay, so we have a removable discontinuity, which is just a hole in the graph. Okay, when we have a hole, the limit exists. The limit exists. However, the function value does not equal the limit. Okay, so the limit exists, but the function value and the limit are different. That's what creates a hole. Okay, so here's a function that clearly there is a hole right here. All right, because right now, if I was to find f of 2 is this point right here, is 10. But if I was to find the limit as x approaches 2 of my function, it would be 5. So the question is, how can f of 2 be redefined to make it continuous? Because right now it's not continuous because these two numbers are different. So in order to make it continuous, I can take this point right here and I can pick it up and I can put it right there. And that would make the function continuous. So in order to do that, I have to redefine f of 2 to equal 5. And if I redefine f of 2 to be 5, then my limit and my function value are the same. And now my limit and my function is continuous. Okay, so removable discontinuities are discontinuities that you can just fill in a hole and make it continuous. The next type of discontinuity is called an infinite discontinuity. In the past, you have called this an asymptote. So asymptotes are infinite discontinuities. And an infinite discontinuity at some x value we either have one or both sides of the limits as infinites. So every time you get a limit that goes to infinity, then you'll have a infinite discontinuity. So for example, if I look at this one, this function here, the limit as x approaches the value of 0 from the right, so looking at this function right here, or this part of the function, you will see that I have a vertical asymptote. So this goes out to positive infinity. And then the limit as x approaches 0 from the left of the function goes out to negative infinity, because it's this portion right here. Okay, this gives me an infinite discontinuity. Every time I have an asymptote, it's an infinite discontinuity. Same thing here. While this portion doesn't have an asymptote, because it just stops right there, this portion does. All right, I can draw this asymptote right down here. And this would still be an infinite discontinuity because I just need one side of the limits to be infinite. And this would have the right side being infinite. So this would be the limit as x approaches 4 from the right of my function. This one is positive infinity. So while the first example had both sides having infinite limits, this one only has the right side. Both of these are infinite discontinuities. So we have removable discontinuities where you can fill in a hole. You have an infinite discontinuity, which is an asymptote, and then you have a jump discontinuity. There will be an actual jump in the graph. So an actual jump in the graph. Okay, and when you have a jump discontinuity, that's where you have only one-sided limits existing, but the limit itself does not exist. So here, if I have the limit as x approaches 4 of my function, well, let's go 4 from the left, and that would be the value of 3. And the limit as x approaches 4 from the right, so we're looking at this guy up here, that would be 8. So because these two limits are different, the left limit and the right limit are different, there must be a jump in the graph. And you can, by looking at the graph, you can see that actual jump. Okay, because the left limit and right limit both exist, right? They both exist, but they do not equal each other. Then you have a jump, and that's what we have here, a jump discontinuity. When you have a jump discontinuity, we have this thing called left continuous, right continuous, or neither. So this only occurs if a function has a jump discontinuity. So if a function has a jump discontinuity, then we can define the continuity as left or right continuous or neither. I'll show you how that works. So looking at this graph, these three graphs, in order for it to be left continuous, that means that the left part of the function has to have the filled in dot. In order to be right continuous, the right part of the function has to have the filled in dots. This is the calculus version of left and right continuous. This is saying that the left limit, right? This is the left limit equals the function value. And this is saying the right limit equals the function value. So if it's right continuous, then it's right limit function value. If it's left continuous, it's left limit function value. Now, looking at a graph, we can just look at this intuitively. Because this dot is filled in and then it goes to the right, this is a jump discontinuity that has right, that is right continuous. okay? Because there's an open circle with the left part of the graph. So it is right continuous. This one, because this dot is filled in, is left continuous. Because the left limit equals the function value. Here, the function value is defined up here, and in this one, the function value is defined down here. This one is neither left nor right continuous, and that's okay. It's allowed to be neither, and that's because both sides of the function have an open hole, and then I have this point in the middle that defines the function value. Okay, so you're only looking at left and right continuity when you have a jump discontinuity, and your function can be left continuous, right continuous, or neither if you have a jump discontinuity. So let's look at this graph here. I want to classify each point of discontinuity as removable, jump, or infinite, and state whether the function is left or right continuous. So let's look at each type of discontinuity. I have a discontinuity here at the value of A. I have a discontinuity here at the value of B. I have a discontinuity here at 0. And I have a discontinuity here at C. So let's start with A. The kind of discontinuity I have at A is infinite. So I have an infinite discontinuity at x equals A. And if it's infinite, then I don't have to deal with left or right continuous. I only deal with left or right continuous when functions have jump discontinuity. Then at the x value of B, here I have a jump discontinuity at x equals B. So now because I have a jump, I have to decide, is it left continuous or is it right continuous? Well, the dot's filled in here and it's going off to the left, so therefore it is left continuous. Okay, then I have my discontinuity here at the x value of 0. And this one is just a hole removed. So this is a removable discontinuity at x equals 0 because I have a single point removed. That's different than this one here. As you can see, when x is b, I have a jump, it's a physical jump. This one's a single point removed. My limit exists, but the function is defined up here. And last but not least, at the x value of c, again, I have a jump discontinuity. And because I have a jump discontinuity, I have to decide whether it's right continuous, left continuous, or neither. And because neither of these are filled in, it is neither left nor right continuous. And that's how we look at a graph and decide what kind of discontinuities does it have. Okay. Here, we now have functions. So with these functions, I would like to talk about what kind of discontinuities I have. So when we're looking at this function, g of x, I can rewrite this as 1 over x minus 1 times x plus 1. And what you should have learned in your previous math classes is that when my denominator is 0, I get vertical asymptotes. All right, so I have a vertical asymptote at x equals 1 and x equals negative 1, which means in calculus, I have an infinite discontinuity at x equals 1 and negative 1. And if you don't believe me, go ahead and input that function into Desmos, and you will see that I have two vertical asymptotes, one at 1, one at negative 1. Okay, it would look something like this, with an asymptote at negative 1 and an asymptote at positive 1. And then my function probably looks like that and that. Then in the middle, It's even, so I think it will look like something like this. I think. Like that. Okay, and you have my two vertical asymptotes. Here, I have to factor this. Okay, so let's look at f of x. So I have, if I was to try to factor this, I would end up with -2, okay, -4, -3, so that's -4 and 1. So this would factor to 2x squared minus 4x plus x minus 2, which gives me 2x, x minus 2, plus 1, x minus 2. All right, so this ends up factoring to 2x plus 1 times x minus 2 over x minus 2. And what you'll notice that's very different than the first function is that x minus 2's cancel out. And when you cancel things out, you don't get an asymptote. In fact, you get a hole. So there is a removable discontinuity at the x value of 2. Now, how did I get this 2? Well, that is because it is the 0 of the common factor that I've canceled out. So because I canceled out x minus 2, there must be a hole at the x value of 2. Okay, so this function looks something like this. It would look like this, and at the x value of 2, there would be an actual hole, and then it would keep going, like that. Okay, which is different than the first one, because the first one, nothing canceled out, and that's why it was infinite and not removable. When things cancel out, you get removable discontinuities. So in conclusion, we have three types of discontinuities. We have removable, we have infinite, and we have jump. And we have to be able to look at a graph and decide which of these three types of discontinuities we have. If we have a jump discontinuity, we could be left continuous, right continuous, or neither. Okay, I will see you next time in our calculus lesson.